Okay, so let's get started with the first talk this morning. And the talk is the string duo free and equal 4 supermills by Matthias Gaberdiel. Please start.
Okay, thank you very much. Thank you very much for the invitation to come here. It's always nice to come to this wonderful place. So what I'm going to talk about is work I've been doing over the last quite a number of years by now, together with Rajesh Gopakuma. And it's about trying to understand or really derive the ADS-CFT duality. So let me remind you what the challenge is in doing so. And this is a very schematic, but in fact, that was already mentioned by Fernando Alda in the first talk, on the first day of the conference. So the challenge is in the way the parameters of the two sides are related to one another. So one part is relatively easy, the string coupling constant, the measure for how much strings join and split, is related to 1/n, the rank of the gauge group in the dual DFT. So we'll be interested in the larger n limit, which means where the gauge theory simplifies, and that's also the regime where the string coupling constant becomes small. So that's a no-brainer. We clearly want to first look at the larger n limit. The other to the TUF parameter, the effective coupling constant in the larger n limit. And the relation is roughly that the radius of the ADS space or the sphere in terms of the string length is proportional to the TUF parameter, the coupling constant of the dual gauge theory. And this is where people usually say that the ADS-CFT correspondence is a strong weak duality, because if the TUF parameter is small, then the radius is of the same order of magnitude as the string length. This is very far from the supergravity regime, where string theory is where one can use supergravity, approximate string theory, and has good quantitative control. On the other hand, if you want to be in the supergravity regime, if the radius is large relative to the string length, the string is very, very small, then the gauge parameter, the coupling constant of the dual gauge theory is large. And therefore, you're in a regime where one side you have under quantitative control and the other one you don't. And whenever you're in a situation like that, that means it's essentially impossible to prove, because you can only calculate one side and the other side you can't. And therefore, it's very difficult to prove that the two things agree. So what's our idea for how to overcome this hurdle? Now, the idea is that we basically have no choice but to look at a regime where the gauge theory is weakly coupled. And then we just try to make the best of the fact that the radius is small in terms of string units. And we see what we can harvest about this regime. This regime is often referred to as the tensionless regime, tensionless string regime, because what it means is that the radius is of the same size as the size of the string. The string is very, very large relative. I mean, it's as large as the space in which it propagates. And what this means is that its string tension is very, very small. It's a very floppy string, a string that sort of wanders around in this space and has a zero tension or a very, very low tension. And as a consequence, as was already observed many, many years ago, you would expect this to be a regime where string theory has additional new symmetries that reflect in some sense the additional symmetries of a free or weakly coupled gauge theory, and I mean in particular higher spin symmetries. You expect this to be in some sense the maximally symmetric point of string theory, although it's very, very far away from the point where we usually quantize string theory, which is more inspired by some sort of supergravity approach. Anyway, so what our idea or what our proposal is that what we should look is at this weakly coupled gauge theory. And this is due to this tensionless string by this dictionary. And as I said, this is very stringy, very far from supergravity, but it probably has additional symmetries. And you may hope that because of these additional symmetries, there should be some redeeming feature also on the left-hand side. There should be something special that allows you to get this theory under control. And our basic idea is that while it won't have any simple supergravity description, maybe it actually has a very simple worldsheet description. Maybe what's special about the fact that this is effectively a free theory is that when you describe this string theory like a string theorist, I mean, this is something people don't do these days anymore, but if you think back about your youth when you still went Green, Schwartz, and Witten, then you could believe that maybe there is actually a solvable worldsheet description that allows you to describe the string theory regime that should be dual to free super-Yang-Mills. Now, this is a bold guess. The bold guess is basically inspired by the fact that there's so much symmetry here. There must be something special here. it's clearly you have to describe it in terms of the worldsheet description. So the worldsheet description must somehow also be simple. And what's the most simple thing you can have? Well, it's a free field theory. So maybe if you're lucky, there could be a free field worldsheet theory that is dual to weakly coupled or free super Mills. Now, this is just ideology or advertisement talk. So what's the basis for this claim and for this idea? Well, I think we would say that for the case of ADS3 cross S3 cross T4, we have very, very good evidence, and I'll try to review this briefly in this talk for the first half of it, that this picture is indeed realized. So what may I remind you about the status of ADS3 cross S3 CFT duality? So the generally accepted wisdom is that string theory on ADS3 cross S3 cross T4 is dual to a conformal field theory. That's the full phrase is sort of the politically correct way of saying it, is that it's on the same moduli space of conformal field theories as the symmetric orbifold theory itself. And the symmetric orbifold theory is just the theory T4 to some nth power divided by the symmetric group. So this is a specific conformal field theory. And the statement is specific conformal field theory has many marginal operators. So it sits at some point in a moduli space of conformal field theories. You can perturb it and walk around this moduli space. And any point in this moduli space is dual to some strict background in ADS3 cross S3 cross T4 and conversely. So there's a one-to-one correspondence between string theories on ADS3 cross S3 cross T4 and a conformal field theory that lives somewhere on this moduli space. Now, in order to see to which extent this fits in this pattern, you have to understand what's the analog of free or weakly coupled super Mills in this context. And the natural analog is to believe that it's the symmetric orbifold theory itself, because the symmetric orbifold theory is essentially a free theory. The only constraint you impose is this global orbifold constraint, and that's a little bit like the gauge singlet constraint of n equals to 4 super Mills. So the idea is that the analog of free super Mills in this context is the symmetric orbifold theory itself. So what you would hope is that the symmetric orbifold theory has a string dual description in terms of a worldsheet theory that's effectively free. At least that would be if our idea is realized. And what we claim is that it is in fact dual to a very specific string theory. This string theory you can describe in the so-called hybrid formalism of Berkowitz, Waffer, and Witten in terms of a Wessel-Witten model based on PSU 1,1/2. But the special point that corresponds to the symmetric orbifold theory is the point where the level of this Wessel-Witten model, this affine Kac-Moody algebra, is at level 1. And now, if you know a little bit about affine Kac-Moody algebras, you know that low-level theories are sometimes much simpler than generic level theories. So, for example, SU2 at level 1 is equivalent to a free boson. And in the very same spirit, what one can show is that PSU 1,1/2 is in fact has a free field realization in terms of 4 symplectic bosons and 4 free fermions. And I'll explain in more detail later on exactly what I mean by that. So this is a very specific worldsheet theory, and you have effectively a description in terms of free fields. So this is a theory where you can calculate anything you ever want to calculate. And the claim is that this worldsheet theory, if you treat it as a standard worldsheet theory, if you calculate the physical space-time spectrum, that you reproduce exactly the single particle degrees of freedom of the symmetric orbifold theory. And furthermore, we don't just reproduce the spectrum, we also produce the structure of the correlation functions of the symmetric orbifold from this worldsheet perspective. So in this example, we really have a lot of evidence, and I'll try to briefly review this for you in the first half of my talk, that this correspondence is exactly realized, and it's of this kind that I was outlining first earlier. Now, earlier this year, we tried to generalize this to the case that would be dual to free super Mills in 4 dimensions. Now, obviously, there we are a little bit on our own, and there is no Berkowitz, Waffer, Witten type hybrid formalism for string theory in ADS5 cross S5, but by analogy with work for ADS3 cross S3, and by the fact that this has a twistor space type interpretation and various pieces of evidence, we came to the conclusion that the correct worldsheet theory would be the worldsheet theory that basically contains twice as many symplectic bosons and fermions. And they, in fact, produce for you a free field realization of PSU 2,2/4, again at level 1. And that is a natural algebra to appear because that is exactly the global symmetry of n equals to 4 super Mills in 4 dimensions. So that shows you that maybe you are on the right track. Now, again, there's spectrally flowed representations that I'll explain to you later on. They play a key role. And what we've shown, this is the result of earlier this year, that while we haven't got a complete description of how to quantize this model, there's a natural prescription for what this should amount to. And if you follow your nose, then you can exactly reproduce the spectrum of free n equals to 4 supermills from this worldsheet theory. So therefore, we believe this is a very plausible candidate to be the correct string description that's exactly dual to n equals to 4 free supermills. And if this turns out to work out, then this would really open the door towards proving the ADS-CFT correspondence in that context. Because you see, this is an explicit worldsheet theory that you can calculate and control and analyze to your heart's delight. And it's meant to be dual to another theory you have under complete control. So it has turned this allegedly strong weak duality into a perturbative duality where you have both sides under total explicit control, and you should be able to prove that they are exactly equal to one another. So this opens the door for deriving the ADS-CFT duality in the 4-dimensional case at this very specific point in moduli space. Now, obviously, if you understand the duality at one point in moduli space and the full theories match, then you can also perturb them away on both sides. That would effectively prove for you the whole duality everywhere in moduli space. So this is sort of the vision of how we want to try to approach this problem. Okay, so this was my slightly longish introduction and motivation. So let me first try to review for you the state of ADS3, because that will set the stage for what we'll do later for ADS5. Then I'll explain to you how the generalization to ADS5 works, and then I'll end with some conclusions. So as I mentioned before, at ADS3, you can describe the theory in terms of this hybrid formalism, which means a Wessel-Witten model based on PSU 1,1/2. That describes the ADS3 cross S3 part. Then you have a T4 part that you describe in terms of a topologically twisted sigma model on T4, which is just a fancy way of saying that you have 4 free bosons, and the 4 free fermions originally were all spin-1/2 fields. Half of them become spin 0 and half of them become spin 1. That's basically what this means. And it's been checked that this theory, this is an equivalent description to the more familiar Maldaceno-Auguri description, but at level 1, it still makes sense, and that's the correct description of this level 1 background. Now, as I mentioned before, this level 1 theory has a free field realization in terms of what I called symplectic bosons and real fermions. So the fermions are just fermions, so that's what you all recognize. So epsilon alpha beta is just the epsilon symbol, which is plus or minus 1. And then the bosons are spin-1/2 bosons, which is the reason why you call them symplectic bosons. You see the right-hand side looks exactly like a fermion, except that you have commutators rather than anti-commutators. So this is what you call a symplectic boson. You could also call it a ghost, whatever you want to call it. That's what the free field theory consists of. And then you look at essentially all the bilinears of these things, and then you realize that they produce for you U1,1/2, which is in super Lie algebra at level 1. And then in order to reduce this to PSU 1,1/2, which is what we are interested in, that's what underlies the Berkowitz-Waffer-Witten description, you have to gauge by this diagonal U1 field, which is basically bilinears in the symplectic bosons and bilinears in the fermions. Now, what are the representations? So this describes sort of the chiral algebra, if you wish, of this worldsheet theory. So what are the representations that this theory is made of? Now, free fields have free field realizations, free field representations. And for free fields, there's not that much you can do. So you can either put all the fields in a Neveu-Schwarz sector, I mean they're all half-integer moded, or you put all of them in the Ramond sector, I make all of them integer moded. And in either case, there's just essentially a single highest weight representation, because the ground states are killed by the positive modes and the negative modes produce everything there is. So there's basically one representation. So this is a picture of the Ramond sector representation, which will be, in some sense, the more interesting representation in this context. And the Schwarz sector representation isn't really part of this worldsheet theory. And here, so I illustrated the J30 and L0 eigenvalue. These are the eigenvalues of the conformal dimension and the Cartan generators of the SU1,1. And it's basically infinite in the J30 because the symplectic boson 0 modes move you all the way to the right or all the way to the left. You see, if there were fermions, they would produce for you a finite dimensional Clifford algebra representation, because a fermion you can apply at most once, but a symplectic boson you can apply as many times because it satisfies commutation relations rather than anti-commutation relations. So this is basically what this representation looks like. And the ground state form what you may call the singleton representation of PSU 1,1/2. That's just for people who've come across these types of representations before. Now, this theory would be a little bit boring. And in fact, that doesn't describe the correct string theory. And that goes back to the work of Maldaceno-Oguri, who noticed that in order to describe string theory in ADS3, you have to introduce representations whose L0 spectrum is unbounded from below. This is, in fact, what you should be familiar with also in flat space. You see, when you describe string theory in Minkowski space, the Fock space also has an unbounded L0 spectrum, because you see, you need arbitrarily negative eigenvalues of L0 so that you can have very high excitation and still satisfy the Maschel condition L0 is equal to 1. So your L0 spectrum must necessarily be unbounded in order to get the rich structure of string theory. So what Maldaceno-Oguri proposed is that what you have to do is you have to add in spectrally flowed representations, starting from these conventional highest rate representations. And what this means is, it's a bit of a fancy way of describing it, but basically there is a pretty trivial automorphism of these three fields where you move their mode numbers up and down. And given the simple structure of the commutation relation, that's clearly an automorphism of this algebra. And then you start with the representations, the standard Ramond sector representation with respect, say, to the tilde modes, and you interpret it with respect to the action of the untilde modes. And because this shift in this mode number, what happens is that what used to be a highest rate representation doesn't become a highest rate representation anymore. In particular, if you calculate the L0 eigenvalue in terms of the tilde L0 eigenvalue, you have this relation. And from this, it's clear that if you go far to the right, the L0 eigenvalue become as negative as you want. So you get an unbounded spectrum with respect to L0. That's just essentially the prescription of Maldaceno-Oguri translated into this hybrid formalism. But what's key is that these are not highest rate representations, and these are the representations we will need in order to capture the entire string spectrum of this background. Now, this is the representation. So now you have your worldsheet theory. You have the chiral algebra, you have the set of representation, namely the Ramond sector plus all its spectrally flowed images. And now you simply follow the rules of Green-Schwarz-Witten. You look for the physical states, you impose the Maschel condition, and you simply enumerate how many states there are that satisfies these conditions. Now, since these level 1 theories are much, much more constrained than regular theories, they have many, many null vectors. And effectively, if you look at their character, they really only have 2 bosonic and fermionic oscillating degrees of freedom. Whereas naively, you would have expected this to have 6. You see, SU 1,1 is a 3-dimensional Lie group. SU 2 is a 3-dimensional Lie group. So generically, you would expect this to describe a 6-dimensional geometry, namely ADS3 cross S3. So naively, you would have expected to have 6 bosonic oscillating degrees of freedom. But just like for SU2 at level 1, where instead of having 3 degrees of freedom, you only have 1, for PSU 1,1 / 2 at level 1, instead of the 6, you have 2. That just turns out from the representation theory of this super Lie algebra, or affine super Lie algebra. Now, in string theory, once you impose the physical state condition, you basically know that this will kill 2 bosonic degrees of freedom for you. So if this only has 2 bosonic degrees of freedom to start with, and you kill 2 bosonic degrees of freedom, then you have no degrees of freedom left from ADS3 cross S3. And the only degrees of freedom that will survive are those that come from the T4. And the fermions counting work similarly. So what you're going to get are degrees of freedom that are entirely associated to T4. And if you go through the exact structure of it and determine the space-time conformal dimension, then you find that the physical degrees of freedom on the worldsheet reproduce for you exactly the spectrum of the symmetric orbifold of T4, or to be more precise, the single particle part of the spectrum of the symmetric orbifold of T4 in the large n limit, where for people who know what the symmetric orbifold looks like, the W cycle twisted sector comes from the sector with W units of spectral flow, I from the sector where we have applied W times this automorphism that I described here. So this tells you that this worldsheet theory produces exactly the spectrum of super Yang-Mills theory, not super Yang-Mills, of the symmetric orbifold theory from the worldsheet perspective. But in fact, also the worldsheet correlators come out correctly. And this is a very intriguing observation that I'm trying to capture on one slide. So this is maybe a little bit of a cramped slide. But the basic idea is that if you calculate the correlators of the symmetric orbifold theory, So this is captured here. So this is a sphere. The boundary of ADS3 is a cylinder. So if you compactify it, it's a sphere. You insert vertex operators on it, which are the vertex operators of the symmetric orbifold theory. Then there's an old idea due to Lunin and Matur for how to calculate these correlation functions. And the idea is that you lift this to the covering map, where you sort of undo the twist around each of them by going to a covering map that covers each of these points W many times. So Lunin and Matur explained that you can calculate these correlators in terms of maps from some Riemann surface down to the surface on which your correlators lift. And these covering maps have to have the property that they have a critical point of degree W near the point where you map to the xi downstairs. So that's an observation purely in terms of the symmetric orbifold. But what Pachmann, Rastelli, and Razamet observed was that the most natural interpretation of this is if this map is really, if the covering surface is to be identified with the worldsheet, because the 1/n structure of these correlation functions is exactly captured by the genus of this putative covering surface that appears in the construction of Lunin and Matur. So this suggests that you want to think of this as the worldsheet, and what this would suggest is that your worldsheet correlation function should somehow localize to those configurations where you have this covering map to map you down to the space-time correlator that you are trying to work out. And this is something which we in fact could prove, that is worldsheet correlation functions, quite unlike for a normal CFT correlator, are in fact mostly zero. They're not rational functions. They are proportional to delta functions. And the delta functions select out the ZIs on the covering surface in such a way that this is compatible with this holomorphic covering map. The existence of the holomorphic covering map is a very strong constraint. It's a finite problem. There are only finitely many such covering maps. And therefore, what this means is that this correlation function becomes the sum of delta functions. And when you then do the integral over the worldsheet moduli, you recover exactly the sum over all the covering maps, and thereby reproduce manifestly the structure of the symmetric orbifold correlators. So this is as you can see, I'm quite attached to this construction. I think it's very, very pretty. It's a very elegant way of reproducing this complicated structure of the symmetric orbifold from the worldsheet. And I think this is at the heart of making this work. And as I'll try to explain to you in my remaining 12 minutes or so, the same sort of structure should appear for the case of ADS5. Okay, so this.
Just a curiosity, is there some way of thinking about this as a monodromy that comes from some equation, some auxiliary equation? Since these, these points have some kind of WI would determine some monodromy if you go around them.
Right, but I mean, it's geometrically that you want to unwind this W cycle twisted sector. But you're saying that there's some auxiliary integrable type system whose spectral curve is something like that.
Yeah.
Yeah, maybe. Yeah, I mean, in fact, in the limit where you take these twists to be very large, you can write it in terms of a matrix model, and then this is the spectral curve of a matrix model. So there are situations where this is realized. In general, we don't have a direct understanding of it, but absolutely, that would be interesting to understand whether one can see this structure emerging in some other way other than just as a trick of solving the symmetric orbifold correlator.
Yeah, and in particular, since then if you want to extrapolate it to finite values of the coupling, I mean, maybe this other perspective would persist or something like that.
Yeah, so we are trying to understand the structure of this. I mean, there's intriguing facts about this. So there's this stable differential way of Rajesh of characterizing the points in moduli space. The stable differential seems to be very closely related to the Schwarzian derivative of the covering map. So we are trying to see whether there's a way that this picture would also work at finite W.
But that is related to the monodromy problem.
Yes.
That has this, I forget now what the name of it is.
But somehow this doesn't, I mean, I'm currently looking at this together with a master student. Unfortunately, it doesn't quite seem to be true at finite W. But my hope is that one can characterize the stable differential in terms of the covering map, maybe not quite the Schwarzian derivative, maybe some correction terms. But sure enough, there must be a more direct way of getting at this. At this moment, this is just sort of comes a little bit out of the box. You know, Lunin and Matur tells you that's how you can calculate it. That's somehow also what appears on the worldsheet, but it's a little bit not so obvious exactly how this comes out.
Yeah, thanks.
I mean, the only semi-obvious way of seeing how this comes out is that the way you prove this delta function localization property is that you prove this remarkable identity for these correlation functions. So here are your vertex operators. And if you insert inside the vertex operators a combination of the symplectic boson fields as a function of Z, and you combine it, this linear combination with the covering map, then you can show that the physical correlators are identically zero. So what this tells you is that this covering map lives on the locus defined by this equation, but this equation looks exactly like the incidence relation in twistor space. So you think of the xi plus and the xi minus as twistor variables, and then the ratio, the relative coefficient of them determines the space-time point. So that's the twistor description of the space-time sphere. And somehow this appears very naturally from this perspective. And what it suggests is that the symplectic bosons, their role in life is to describe the twistor space of, in this case, the 2 sphere. And in the case of ADS5 cross S5, probably it's twistor space of the 4th sphere. Indeed, so this is what motivated us. This observation, these various pieces of observations motivated us to try to see whether a similar idea could also work for n equals to 4 superhang mills. And there are various pieces of evidence that led us to consider this model to basically just double the symplectic bosons and fermion degrees of on the world sheet. One argument is that this leads to U2,2/4 level 1, which after demoving a U1 gives you PSU 2,2/4, which is the global symmetry of n equals to 4 superhang mills in 4 dimensions. The other argument is due to the fact that this looks very similar to the twistor space theory that Berkowitz had proposed many years ago, except he had also other degrees of freedom that do not appear in our picture, and he didn't have spectral flow, so his theory didn't quite work. But it's natural to write down these fields as being the twistor fields. There's also, in fact, this is the way you can describe the ambi-twistor of ADS5 cross S5. So there are various pieces of evidence that seem to suggest that this is a natural candidate for your world sheet theory. So at the end of the day, what we propose is that we have 8 symplectic bosons, so 2 + 2 and 2 + 2, they're conjugate to one another. And then you have 4 + 4 fermions that are just standard real fermions. It's basically doubled what you had for ADS3 cross S3. Now the bilinears of this give you U2,2/4 at level 1, and you obtain PSU2 by gauging the overall U1 field, which in this language is just the diagonal combination of the y's and the z's. The y's are the daggered nodes, the z's are the undaggered nodes. And in fact, that this gives you PSU 2,2/4 is something you can read up in Niklas' thesis. This is really the affinization of the oscillator construction of PSU 2,2/4 that plays a prominent role in the spin chain description, which is another point of contact where you feel you're making contact with something that should be relevant in this context. So it's not difficult to see that this gives you exactly PSU 2,2/4. Now, as for the case in ADS3, we have to have spectral flow. We propose there should be spectral flow. And so our intuition here is that the amount by which you spectrally flow these fields up and down is determined in the case of ADS3 by the eigenvalue of the SL2 generator, which becomes the space-time conformal dimension, and the SU2 Cartan generator, which becomes part of the R symmetry of the space-time theory. Now for ADS5, what we propose is that we replace J30 by the dilatation operator in n equals to 4, which is the analog of L0 in 2 dimensions. And we pick a specific R symmetry current. Which one you pick is a little bit unimportant, but you just pick one of them. And that then tells you how these various fields get shifted up and down as you perform the spectral flow automorphism. And then you just run your machine as before. So here it's slightly more convenient to start with the Navier-Schwarz sector, but again, it doesn't really matter. So you start from the standard Navier-Schwarz sector representation of these 3 fields. So this has one ground state and all the negative modes create and all the positive modes kill. And then you interpret it under the spectral flow. So under spectral flow, certain modes do not kill the ground state anymore. And in fact, you can simply read this off from here. So for example, if you look at the mu modes, you see the mu tilde modes with R equals to half kill. So this means the mu modes with a half plus W/2 kill. So they kill if their mode number is greater or equal than W plus 1/2. And likewise, you determine this for all the other generators. So this tells you which modes act non-trivially on this ground state and which modes act trivially. And then so this is a free theory. So the world is subdivided in the good ones and the bad ones. So the good generator depends on what you call good or bad. So one half of the generator kills and the other half generates freely. So those that don't kill generate. So so if these modes are zero, then the complementary set of modes is non-zero. So you can organize it by saying it's all the modes from the first line where R lies inside this wedge, and then all the modes from either the first line or the second line if R is sufficiently negative. So this is simply describing which modes do not kill this ground state. And then our proposal, and this is where we go out on a limb, this is not something we have derived from first principles so far, but what we postulate is that this theory really has some sort of critical n equals to 4 string, and the effect of imposing the physical state condition will be to remove all out of the wedge modes. I mean, if you impose an n equals to 4 critical string condition, you would expect to remove 8 bosonic and 8 fermionic degrees of freedom. So essentially nothing should be left. Now, if truly nothing would be left, then you would not certainly not reproduce n equals to 4 supermills. But given the structure of this mode action, what we propose is that it means that all of the out of the wedge modes gets removed by the physical state condition, and you retain these wedge modes, which we want to think of as generalized zero modes. This is also fitting together with the description of some of these flux solutions of the Berkovich string of Dolan and Goddard and Nail. And furthermore, we expect that because there are effectively zero modes, that only one copy of them will survive. So you don't have a separate left mover and right mover fermionics, these zero modes, but only one set of them survives. So this is the proposal, that the physical state condition is everything you can make from these modes, from one set of these modes inside this wedge. And then you still have to impose some residual gauge condition. You clearly have to impose that this C condition is still satisfied. That's the condition that brings you from U2,2/4 to PSU2,2/4. And then in addition, we propose that there is some mesh shell condition that's left behind. And the mesh shell condition should take the form that L0 is a multiple of W in the W cycle twisted sector.
Sorry, why is it difficult to give the first principle derivation in this case?
Well, I mean, what we would have to do is we would have to construct the core. I mean, in Berkovich-Vafa-Witten, they constructed a cohomology, and you would have to first define what the operators are that define the cohomology and then solve it. Now, even for Berkovich-Vafa-Witten, nobody has actually solved the cohomology beyond.
It's a well-defined question, but you have to solve it, I see.
Well, but I mean, we don't even have yet written down what the cohomology operators are. So,
I see.
So we propose that there is an n equals to 4 algebra whose cohomology would reproduce that. But I think, I mean, given the fact that it works, we would argue that there's bound to be such a construction, and it's just yet to be found exactly how it works out, but we haven't yet worked it out. So this is the proposal, that the effect of it will be you only keep these wedge modes, and then you impose this residual gauge condition, which seem relatively reasonably motivated. And then our claim is that if you do this, you reproduce exactly the spectrum of free n equals to 4 supermills. Now, this is something you can prove. That's in fact not that hard. The idea is that these wedge modes you won't think of as being the momentum modes that you can inverse Fourier transform to give you position modes. So if you define the position modes by this formula where these were the wedge modes you had before, then you can show that these position modes are localized to one of the W positions. So it starts to look like a spin chain with W many sides. Then at each side of this spin chain, you have the generators Zi and Yj at each separate position. And at each position, they satisfy the usual algebra. And if they sit at separate positions, they commute with one another. And then this residual gauge condition, you can convince yourself what this is equivalent to. This is imposing the condition, the corresponding localized C condition at each of the sides. And then by the usual oscillator construction that tells you at each side you have a singleton representation of PSU 2,2/4 sitting. And this mesh shell condition basically just gives you cyclic invariance. So what you're going to get is W many singletons modulo the cyclicity condition. And as has been known for many years, that's a way of describing correctly the spectrum of free supermills. So this is how this comes about. So once you've accepted that the physical state condition amounts to just keeping the wedge modes and retaining these residual gauge conditions, you land on your feet. And what you see is that the super-Yang-Mills fields that involve W letters, where each letter is an element in the singleton representation, i.e. a scalar or a fermion or a field strength with arbitrary derivatives, is exactly accounted for by the physical degrees of freedom that come from the W spectrally float sector of this free field theory. So this looks like a twistor-valued string bit model for this string theory, and it's the natural generalization, in our opinion, of what demonstratively works for ADS3 cross S3. So we believe that is a very good candidate to make to be the worldsheet dual, the worldsheet theory dual to free super-Yang-Mills. I think I'm a little bit running short of time, so there's a way of sort of systematically producing the spectrum, and I can answer upon questions if people want to know more details. But let me conclude by saying that the free field realization for the ADS3 cross S3 worldsheet theory is dual to the symmetric orbifold theory that we've really checked. There's a prescription of Berkowitz-Vafa-Witten. In principle, it's clear what you have to calculate, and there are numerous checks that support the idea that this matches exactly the symmetric orbifold. We think this has a very natural generalization to ADS5 cross S5. This generalization has the property that if you postulate what we believe is a plausible way of characterizing the physical state condition, you reproduce exactly the spectrum of free super-Yang-Mills in 4 dimensions, and we feel that opens the door for proving the ADS-CFT correspondence, because it gives you a worldsheet theory that plausibly will be exactly dual to free super-Yang-Mills, and therefore it turns this problem into a field redefinition perturbative duality type problem, which one should be able to prove. Now, there are obviously many, many things for the future. So first and foremost, we have to understand this physical state condition from first principles. We have to construct this cohomology operator, show that the cohomology leads to that. Unfortunately, that's not an easy problem, but we are working on it. Then we are trying to understand the structure of the correlation functions. And if you remember how this worked for ADS3 cross S3, you see you had 4 symplectic bosons, and the covering map came from the 4 symplectic bosons. Now you have 8 symplectic bosons. So how much worse can it be? So this is what we are currently working on. Now, it is a little bit more complicated because you see you have to have a holomorphic map from a Riemann surface, your worldsheet, now not into a 2-dimensional Riemann surface, but into a 4-dimensional space. So you have to understand what's the analog of the covering map. And we are struggling a little bit with that. There are some maps from CP1 to CP3 with various properties, and we are trying to understand exactly what characterizes that. So far, we've only analyzed the free case, but obviously what you would like to do is perturb away from it and show that you reproduce the anomalous dimensions of n equals to 4 from a worldsheet perspective. And I mean, once you've understood how the correlation functions work, this should be relatively straightforward. And our hope would be is that while we would not want to reproduce every calculation independently, what you would hope is that the worldsheet theory will localize to become a spin chain calculation. So that in some sense, you would manifestly reproduce the correct answer, just like you did in the symmetric orbifold theory, where the worldsheet theory localized to become something which is the way of calculating the symmetric orbifold. Then there's the questions of, so this is all purely perturbative, so one can ask about non-perturbative effects. So we wrote a paper recently with Jakob and Bob, and there was a paper by Alex and his friends on related topics, where we see the first instances of how the deep brains of this worldsheet theory fit together with in fact, also boundary states of the symmetric orbifold. It would be interesting to understand the higher spin and the Yangian symmetry that must somehow be deeply embedded inside this worldsheet theory. It would be interesting to bring this, make this more transparent. And then, yeah, so then there are other things that this suggests maybe slightly novel views on how to calculate n equals to 4 super-Yang-Mills, but in view of time, I'll stop here and thank you for your attention.
Okay, now time for questions, perhaps on site, yes.
Can you say something about finite temperature for ADS5? Is that beyond reach, or?
Well, you haven't really thought very much about that so far. I mean, that is, yeah, I mean, at the moment, we are just trying to reproduce the free spectrum. We are trying to understand the structure of it. We are trying to understand it reproduce the perturbation theory. Finite temperature, we haven't yet thought about.
And maybe then a second question. In the ADS3 case, this grand canonical picture plays an important role, or is a useful trick to compute stuff. Is there going to be something similar for ADS5, or?
Yeah, so I mean, as people probably know, so I think this grand canonical sample has a chance to be true, although I'm not entirely convinced it's necessarily the right way. I mean, I think there is a calculable question of whether this is the correct description or not. I mean, to leading order, it doesn't make a difference whether you say GS is 1 over n or whether you go to the grand canonical ensemble, but to subleading order, that should make a difference. And I think it would be interesting to check whether that really is the correct picture or not. For the symmetric orbifold, I can very much believe that this is the correct picture. I don't believe somehow, yeah, I'm agnostic about it, whether there is a similar picture for ADS5. I think on balance, I'm inclined not to believe so, but I'm an old-fashioned guy, so I'm slow to change my mind about these things.
Thanks.
Okay, further questions? Yes. Oh, I see.
Okay. Well, I can ask my question anyway. How about finite n? Does this produce any finite n spectrum? You seem to be only interested in the planar limit.
Yeah, so this is like for ADS3 cross S3. So in ADS3 cross S3, so what this would mean, because I mean, in some sense, the finite n-ness would come. So for ADS3 cross S3, the finite n-ness would come from the fact that the length of your twisted sector is bounded by n. So this would mean that in the spectrally flowed, from the point of view of the worldsheet, you would only have spectrally flowed representations up to a maximal number of spectral flow. I mean, that's how it works for ADS3 cross S3, right? For ADS3 cross S3, if you look at the symmetric group of Sn, you look at the twisted sectors of it. So these are the conjugacy classes inside Sn. And if you look at the single cycle sectors, the longest one has length n. So in that picture, that would mean that you would have somehow to truncate your worldsheet theory to include only those representations where spectral flow is by a finite number of units. And at least on the face of it, that would not be a consistent worldsheet theory. So what this seems to be is the correct description in the strict large n limit, but reproducing correctly all 1 over n corrections. That's what this symmetric orbifold, the correlation functions implies, because the 1 over n corrections come from the higher genus surfaces, so they do play a role. They reproduce correctly the 1 over n dependence, but you don't quite see the finite n. The finite n from this worldsheet perspective probably has to come from some non-perturbative effects, from things to do with deep brains, but that we don't understand. So this is how we clearly understand how it works for ADS3 cross S3. So my suspicion would be that something similar happens for ADS5 cross S5, but that's obviously very early stages, and obviously their finite n may materialize in some other way, but certainly by analogy with ADS3 cross S3, you wouldn't think that this worldsheet theory would directly describe finite n, because it's really perturbative string theory. So it really describes large n limit, but including all 1 over n corrections. So it's not just planar limit, but it's the perturbative regime around the planar limit rather than finite n.
Okay, so there is time for one more question, for example, online. Oh, yeah, Gerald, yes.
I was wondering, you mentioned just perturbing around the free theory.
Yes.
But I mean, do you have a vision? So can you imagine what will happen if you like really go to finite lambda? So if you do a finite deformation of this worldsheet theory, is it? What happens in the ADS3 cross S3 case?
Well, so in the ADS3 cross S3 case, we're also trying to, I mean, there the correspondence works exactly at the symmetric orbifold point. We know exactly what operator you have to switch on to go away from it, and we are trying to do perturbation theory. Now, in that case, you know that this is very hard to go to finite lambda. I mean, perturbation theory is hard around this point. So I would be happy if I reproduced the first order perturbation theory. So this have a limited expectation at this moment. So I think, I mean, you know, this, I mean, when you say it's on the same moduli space as ADS3 cross S3, I mean, this is, these are nice words, but you understand this moduli space at exactly one point. namely the symmetric orbifold point itself, and then you understand the perturbative neighborhood around it. There are no results known anywhere in this moduli.
Could you imagine, so you will have a 2D world sheet theory with some specific deformation, so you know the action. Could you imagine that perhaps you could treat some part numerically or something, but work directly?
Maybe, yeah. I mean, at this moment, I think we are a bit not quite there yet. We have to sort of first, I mean, this theory is a little bit tricky. We have to try to understand how really to calculate correlators. But I mean, for ADS3, we managed to do this. I mean, I feel this is like ADS3 was 2 or 3 years ago. So maybe you come and ask me again in 2 or 3 years.
Okay, thank you.
Okay.
At the next Ascona meeting, indeed. Yes.
Oh, next meeting. That
If they are kind enough to invite me again.
Okay, great. So I think time is up. So let's thank Matthias again.